Hi, and welcome back to the shop. Today we aren't going to be producing any parts. I'm going to be answering questions. Questions that I think may be of interest for other people. Now, I do get a lot of questions, and sadly I don't have the time to answer all of them. But I do answer some of them, and I will answer the ones that we'll present today. And we're going to start with a question from Frank. I don't give full names, but we'll just say Frank. Frank wants to know how I'm going to measure or do the quality control on that 45-degree angle that we produced on the part that we made in the last video, which was the part 2 of our Drigs and fixtures video. Well, that had a 45 degrees. Now, if you have a comparator, an optical comparator in your shop, and I would be very surprised if you did. But if you did, well, that's really the best way of doing it, because you'll be able to measure angle and position in one foul swoop. But people just don't have that. And angles are a problem. We've mentioned this in the metrology course. And that is that you have to measure two things to get the angle. There's the angle itself, and that's what Frank wants to know. And then there's the angle's position in space. And well, that's Michael's question. Now, Michael wants to know how to measure where that angle is. In other words, for the part we produced, that 1.13 dimension. And well, that's a little complicated. So, to take care of things with angles, we divide and conquer. So we're going to measure our angle first, and we're going to determine its position after, once we know that the angle is good. And for measuring the angle, well, we're going to be using our surface plate, a surface gauge, a dial indicator, and a V-block, a 90-degree V-block, and we're just going to swipe the angle. If you do this carefully, it can give really good results. Once you know that the angle is good, well, now you have to find its position in space. And that, well, is, like I said, a little more complicated. So let's head over to the whiteboard and let's do the math. Now, once you know that your 45 degree is okay, well, then you can think about measuring. And what we want to know here is this 1.13 dimension. How do I measure from a surface to an inclined surface? I can't use calipers. I can't use a micrometer. So what am I going to do? Well, I am going to use a micrometer here, but I'm going to do something before that. And that is, I'm going to project this top surface out and imagine that I'm putting a pin along here, a pin that's big enough to just barely protrude past the face here. If we did that, what would we have? Well, we'd have this here. So let's take a closer look. So let's imagine that our 1.13 dimension, or that corner, is up here, and that's our angle, and here is the other face of the part. So the reference for the 1.13 is somewhere back here. And this is my pin that's nestled into the projected surface and the angle. Now, this pin has a diameter. I haven't figured this out. I'm just showing how to do it. But it has a diameter. And I know that from the center to the end edge out here, parallel to this line, it's going to be 0.5 diameter, half of the diameter. Now I know that from this point to the point perpendicular to the angle is going to be half the diameter also, so 0.5 diameter. And I know up here that it's 0.5 diameter. Now this line is straight, so if that's 0.5 diameter, this is 0.5 diameter, and that, since this is 45, is going to be 0.5 diameter also. What we need to know here to resolve this is this length here, which is the hypotenuse of this triangle. Now we have 0.5d, 0.5d. So I know the two sides, they're equal because it's a 45-degree triangle, and I know that the hypotenuse is going to be a little longer than the two sides. So what am I going to do here? I'm going to go sine of 45, and with sine of 45, opposite over hypotenuse, I can calculate the hypotenuse here. Once I know this dimension, well, I can do 0.5 diameter plus the dimension I just found, plus 0.5 diameter. I know that because if that's 0.5, that's 0.5. And that brings me to the 1.3. So we'd go 1.13 plus 0.5d plus unknown, which is our hypotenuse, plus 0.5d. And that will give us the dimension from the end there of that pin to the back of the part. Now, in what way does that help us? Well, I know that overall dimension. We have the equation equals the overall length. So this is a linear equation, and whatever answer I get there is what I should measure when I measure from the outside edge of the pin to the back of the part. Now, let's say that I measure that, and what I get as a result of that measurement is exactly what I calculated. Well, that means that my 1.13 is exactly 1.13. I know nothing's exact, I just said that. Let's say I measure and I find that my measurement, the one that I've just made, is 2 thou larger than what I calculated. That means that my 1.13 is 2 thou larger, so it would be 1.132. Why? It's linear. It's not an exponential equation here. So anything that I measure that's over the answer will be over the 1.13. Now, that's all fine and dandy, but we don't have a projected surface. And how can we do that? Well, there's a quick and dirty or quick and easy way. Let's head over to the mill and take a look at that. So here's the bottom of the part, and down next to the table I have the top of the part. This is the face that the angle comes up to. So what I want to measure is from this angle here to the back. Now we calculated, here's my pin. So I can install the pin in here. You'll notice that I put this a little at an angle. That's because when I'm going to measure with my micrometer, I don't want the graduated barrel of the micrometer to come into contact with the table. So here we go. And well, there you go. We can measure that quite easily and quite accurately. The next question comes from Ian, and it's a little simpler. Well, it's simpler for me to answer. And that is, Ian wants to know, what make is my shaper? Well, my shaper is probably a little older than I am. And it is a Prima, so P-R-E-M-A. And it was made in Sweden, so it's a Swedish machine. So here's a little trick if you want to measure several pieces and know if your parts are within their tolerance. Now, the measurement here has the tolerance of plus or minus 5/1000ths of an inch. So here's what I'm going to do. I'm going to shut up my calipers, bring myself to 0, and then I'm going to come and set my calipers to the dimension that I'm measuring. And that's 1.350. I'm shaking a little bit here, so I'm having a hard time. Let's try and get it to 350. Oh, come on. There, 350. Set that to 0. And now I come and measure each part. -1. -1. 0. 0. 0. This is -1. And -1. So we see that my parts are the right dimension, and I know that I'm well within my tolerance. Now, I'm using a vernier caliper to measure these parts because my tolerance is plus or minus 5 thou, and this instrument is more than accurate enough to do the job. Well, it's pretty windy out there today, so if you hear some background noise in the video, well, you know why. Now, I showed you that technique or trick because little Al wanted to know which is most accurate, a shaper or a surface grinder. Well, we saw here with the shaper that I could expect plus or minus 1/1000th of an inch. And well, that is really what I would expect on most shapers. However, with surface grinding, I would expect, without paying too much attention to what I'm doing, to be within 2/10,000ths of an inch. And why is that? Well, it has to do with the machine design, yes, but it has more to do with chip formation. Now, when we form a chip, and we saw this in our chip speeds and feeds video, when we form a chip, we have penetration, we have accumulation, we have formation, and we have separation of the chip. All of those four phases are crucial. Now, if you try and cut too thin of a chip, not cut deep enough for the cutting tool you're using, well, you might get a little penetration, you will get no accumulation or very little, and you will never be able to accumulate enough to form and separate the chip. So what do you get? You get a lot of rubbing, a lot of heat, a very poor surface finish because it's partially burnished, and well, you get a melting tool. So that's really not good. So that means there's a minimum depth of cut. With a single lip high-speed steel cutting tool that's well sharpened, I can expect to lift the chip. The thinnest chip that I think I would be able to lift would be 1/1000, and that would be really pushing it. And that is why I would say that with a shaper, plus or minus 1/1000 would really be the most I would expect. However, a surface grinder, the grinding wheel, because of its high speed and very, very sharp cutting surfaces, those crystals are deadly sharp, well, they can lift a chip really down to a 10,000ths, but I would say without paying too much attention to plus or minus 2/10,000ths of an inch, or could lift a chip of 2/10,000ths. So that is why grinding is so much more accurate than most of the other cutting operations. And well, we see that cutting with high-speed steel and cutting with a grinding wheel, well, is not at all the same thing, even if they both form chips in the same manner. Now, keeping with the shaper, there's Mark and Michael. Notice that there seemed to be a lot of deflection or movement on the table of the shaper when I was cutting there. And well, there seemed to be a lot, but I just measured those parts, and you can see that I really had, from one end to the other of the bar, about a 1/1000th of an inch taper. It was really a gradual taper, or incline, of about 1/1000th of an inch. Now, I thought about it, I checked it from every angle, I applied pressure to the table with a dial indicator mounted on it, and well, as you can see, I just measured the part that I produced. That was a long bar at the get-go. And well, there is just about 1/1000 over 8 inches of deflection or movement on the table. So why does it look like it's moving that much? Well, it's because I'm not very good at producing videos, and my lighting for that shot was horrible. And that means that what you're seeing of the table is illuminated and less illuminated depending on whether the RAM is out or in. And that gives the impression that the table is moving very much, but it isn't. Now, UFO Hunter, he watched the thread cutting video, and he had a question about the calculations, because he's going through the calculations that I indicated in the video, and he's not getting the same results. And well, I cannot be sure because I don't know what result he was getting. But I know that when I was teaching, the biggest problem I had with my students, knowing that they had just finished their high school math, was the order of operations. Now, if you haven't been doing math for the past 30 or 40 years, well, it wouldn't be surprising if you didn't follow the proper order or forgot that there was an order. So here's the formula that was in the video. M equals E minus 0.86603 P plus 3W. Now, in that formula, there is no order indicated. Now, if I were doing that in a regular high school course, I would put brackets around what had to be done first. And in this case, we can see on the second line that I have M, which is M max, equals E, which is my pitch diameter, and in this case it's my maximum pitch diameter, 0.5875, and minus, and here I put in brackets, 0.86603 times 0.05555. 555, sorry, a 5 too many there. That bracket means I have to do that operation first. And after we see that we have a plus 3, plus bracket, 3 times a W, which is my wire diameter, and that's 32 thou in this case. So that has to be done as well. So I have to solve both brackets before I do anything else. So multiplications, divisions before adding and subtracting. And in the next line we can see 0.5875 minus 0.04806 plus 0.096. And that means that my maximum measurement over the wires is 0.6354. Now, had I done that in one foul swoop and not respected the order of operations, we can see in the red example here that I would have ended up with an answer of 0.095505. Not at all the same thing. So, the order of operations when you're resolving an equation is very, very important. Mr. Schobar, well, he's getting a little personal, and that's okay. He noticed that I'd lost a lot of weight lately, and I have. I lost about 30 pounds in the past few months. And, well, some of you have also noticed that I've been trembling or shaking quite a bit. And, well, that's even though I've been trying to hide it so much. Now, I'm not going to try and hide it anymore because it just isn't fun. The last video that I produced, the Jigs and Fixtures Part 2, took me a month to produce because I kept reshooting and reshooting because I was shaking, I was having a hard time, and I was trying to hide it. Now you saw when I took those measurements a few minutes ago that I was having a hard time, a lot of shaking. Well, that is nothing compared to what it was like about a month and a half ago. And here's an example of me trying to tighten down the vise onto the table of my milling machine. It is a major problem. And what causes all this? I have always been a very anxious person. It's in my family. My mother was an anxious person, and her father was an anxious person. And being anxious is good. I mean, it's a natural thing. You have to be anxious. I mean, if you're a GNU in the plains of Africa, and you're not anxious at all, you're not going to survive very much, because instead of looking out for a lion here and there, you're going to have your head and nose in the grass all the time, and that is problematic. So we are all anxious. It's a normal thing, but I am excessively anxious. And for me, that was a real good thing for most of my life. An anxious person always is thinking ahead. An anxious person is planning. An anxious person wants to be ready for all possibilities. And when you're a toolmaker, and when I was a teacher, well, knowing where I was going and having a plan A, a plan B, a plan C, and a plan D, well, I really could do my job properly because I was always thinking of options and how and whatnot and what if. Now, anxious doesn't mean that I am shy in any way. I have never had a hard time speaking in public. I actually enjoy it quite a bit. When I was teaching, I always found that I was way smarter when I was in front of the class than when I was sitting all by myself. So that helped me a lot in my career. The problem with anxiety is that if you can work it out of your system, it's okay. I was a workaholic. I used to work and work and work and work. And well, because of that, and maybe because of the anxiety, well, doing that permitted me to be more calm, to live better, because I would work that out with the energy that I was spending. But as you get older, the anxiety doesn't diminish, but your metabolism certainly does. I can tell you, as you get older, you young guys out there, things change quite a bit. And well, that means that the anxiety becomes a problem the older you get. And well, I'm at that point in my life where it is a problem. And well, the good thing is I'm getting better. I still shake, but I shake a lot less. What causes this shaking? In my case, it's a surplus of adrenaline in my system. And my muscles are just working against each other, and they're always overshooting where they want to go. My mind knows where the fingers want to be. My muscles can't bring them there because they're a little overexcited. So that's the Q&A for today. I'm sorry if it got too personal at the end there, but I think it's important. I mean, I want to be honest with the people who are watching my videos. So until we meet again, well, have fun. Be safe. It's so very important. Try not to be too anxious, although it's not something you can control. And well, happy machining.
There you go.